we are ready to start. Let me share my screen. Can you see my screen? Sure.
Yes.
Okay. Okay, we're all here. Wonderful. Welcome to the Ph.D. Thesis Defense of SEYED NOSRATI, or SEYED MASOUD NOSRATI, or the other way. The thesis is entitled Prior Knowledge for Targeted Object Segmentation in Medical Images, and the examining committee consists of Dr. Cassandra Marley, the senior supervisor, Dr. Greg Morey, as supervisor. I'll be representing Dr. Morey today. Dr. Pincan, internal examiner, and Dr. Klaus Tony's external examiner. My name is Mark, the chair. And we'll start off with a short talk. How short?
29 minutes.
29 minutes. Make it 28.
So hello everyone. Thanks for attending my thesis defense titled Prior Knowledge for Targeted Object Segmentation in Medical Images. So I'll start with the question, what is image segmentation? So image segmentation is about partitioning an image into meaningful parts. And why do we segment? So the segmentation results help us to automating the further analysis. So in fact, image segmentation is one of the primary steps toward computer-aided diagnosis, therapy planning, and computer-aided intervention. But obtaining accurate results in medical image segmentation is often challenging, mainly due to noise, low contrast, and object complexity in these kind of images. But still, despite the existence of noise and clutter, clinicians can distinguish different structures. How can they do that? They spend a lot of time in med schools. They learn about the anatomy, so they have some idea about the shape, the appearance of different organs. So these information help them to distinguish different structures in the body. Tons of segmentation algorithms have been proposed, like threshold and region growing, but the application of these techniques are limited mainly due to their sensitivity to noise and clutter. The majority of state-of-the-art segmentation algorithms are formulated as an optimization problem, and that's because in optimization-based techniques, we can incorporate multiple criteria as computing energy terms. We can describe our problem rigorously using mathematical formulation. There are lots of optimization tools out there we can leverage to solve our problem, and we can examine the relative performance of different solutions and pick the best one for our problem. Two aspects need to be considered when we are designing an objective function. One is fidelity versus optimizability trade-off. So fidelity is about how accurate the objective function can model the problem. And optimizability is about how easily we can optimize an objective function and attain global optimum. So often there is a trade-off between these two, and recent researchers are trying to improve both optimizability and fidelity without sacrificing one to the other. The second aspect is time and space complexity. And this is especially important in medical image analysis, especially if we are dealing with hundreds of millions of pixels in microscopic images or large 3D volume scans. So it seems that a good segmentation algorithm has to be faithful or model the problem as accurate as possible, should be optimizable or should be optimized easily, should be fast, especially if you are dealing with real-time applications, and should consume small amount of memory, especially if you are processing a huge amount of data. So what do I mean by being faithful? Let's consider this example. So in this histopathology image, if you want to segment this image only based on its intensity, the results would not be very accurate. But if you know that these glands consist of two regions, one inside another, and somehow encode this information into the segmentation algorithm, the results would be improved dramatically. Another example is segmentation of an endoscopic image. Again, if we rely on color and appearance, the result wouldn't be good. But if we encode some information about the shape and relative position of different organs, the result would be improved. So in this thesis, I'm trying to bridge the gap between expert knowledge and computer science algorithms. So for the rest of the talk, I'm going through my contribution during my Ph.D., mainly focusing on incorporating prior knowledge for segmenting targeted multi-part objects. So in the first contribution, we leverage a variety of prior information to design a rich and faithful objective function to delineate the boundaries of overlapping multi-region cells. In the second contribution, again, we want to solve a similar problem, multi-part object segmentation, but this time we want to improve the time and space complexity compared to our previous method and some existing work. So we leverage a level set framework, augmenting it such that it allows to encode geometrical interaction between different labels. In the third contribution, we turn our attention toward optimizability. We propose a continuous convex formulation, again, to segment the multi-part objects in medical images with part configuration constraints. And in our fourth contribution, we propose an efficient segmentation method to segment intraoperative endoscopic videos in robotic surgery. So particularly, we use some information from preoperative scans as well as some information from the surgical system, and we show how we can encode this information into the segmentation framework to have a good video segmentation. And at the end, I summarize and conclude the talk. So many anatomical structures are better described by a combination of regions, and each region might have different appearance model. And often there's a meaningful geometry between different regions, so geometric interaction between different regions. For example, in heart here, a cardium consists of three regions. Myocardium contains left and right ventricles, where left and right are excluded from one another. Another example is cells. Many cells consist of several regions like membrane, nucleus, nucleolus, one inside another. These kind of interactions often been ignored in previous works. For example, in microscopic image segmentation, even some recent works propose methods based on parameter-sensitive morphological operations or even thresholding. But again, the application of these techniques are limited. Plus, these techniques solve cell segmentation for single region cells only. So adding a multi-region cell would add a little bit of complexity to the segmentation problem, but another layer of complexity is added when these multi-region cells overlap. So again, previous work solved cell overlapping only for single region cells using some post-processing techniques. So in our first contribution, the goal is to segment multi-region cells that potentially overlap. So we use a variety of prior information like shape, appearance, edge polarity, geometry, and interpart adjacency, and design a fitness function such that by maximizing this fitness function, we can obtain the delineation of these multi-region cells. So our fitness function consists of three main terms: shape, appearance, and edge, and two main constraints: geometry and interpart adjacency. The first constraint takes care of imposing containment and exclusion between different regions, and the second constraint imposes minimum and maximum distance between different constraints. So although this fitness function seems to model the problem fairly accurate, but we have two problems here. One, this fitness function is too complicated, it's hard to optimize. And the second challenge is that we need to deal with spatially recurring aspect of cell segmentation. There's not only one single cell in the image, there are lots of cells all over the image, and we want to segment all of them. So for the optimization part, we adopted genetic algorithm as a global optimization tool. So we represented the boundary of cells with a chromosome consists of several genes, including pose and shape parameters. We spread a lot of individuals all over the image, and we let the genetic algorithm define these parameters for us. For the second aspect, we adopted the tribe concept in genetic algorithm. In tribes-based genetic algorithm, the whole population is grouped into several tribes. During the evolution, each tribe is evolved within itself. So basically, every two parents has to be selected from the same tribe. In fact, each tribe is responsible to segment a single cell. So this is how we obtain multiple distinct solutions for our genetic algorithm problem. We tested our method on 2 data sets. Here's an example of an image from a multi-region cell data set. And this is the result we obtained from DeLong and Woodcock's method. This is a graph-based technique that encodes geometrical constraint between different regions, like containment. And this is our results. So it's clear that our method could manage to delineate the boundaries of these overlapping multi-region cells more accurately than DeLong and Woodcock's. And here's another example, graph cut segmentation versus our method. We also tested our method on breast cancer images dataset. This dataset has been used in ICPR 2010 contest. We compared our method with the finalists of this contest, as well as 2 state-of-the-art methods that use the same dataset. So we compared our method with these techniques in terms of detection error and distance error or inaccuracy. So the methods closer to bottom left of this graph are more accurate. So the problem with our method is it's not very efficient in terms of runtime. So it takes a lot of time to spend to segment many cells. So basically, the runtime depends on the number of cells. So in our second contribution, we want to improve the time and space complexity, again, to solve a similar problem. So in this work, we leverage the level set framework. We augment this level set framework such that it allows to encode geometric and distance constraint between different labels. So why we choose level set? So it has lots of good advantages or properties. It doesn't depend on parameterization. It's easy to implement. It can automatically handle topological changes, which is good for cell segmentation. It's easy to extend it to higher dimension, and it's easy to impose different prior knowledge. So our method can encode 2 important geometrical constraints, containment and exclusion. In addition, our method can encode 3 different spatial distance constraints between different regions. Minimum distance, maximum distance, and spring-like distance that's caused by some attraction and repulsion forces. These images shows how surfaces evolve when we apply our method to them. So the image on the left shows 2 regions are contain each other with attraction and repulsion forces. The image on the right shows the evolution of two surfaces that contain each other with minimum and maximum distance between them. And the bottom image shows 2 surfaces that are being excluded from one another with a specific distance between them. We extended our method to handle any arbitrary number of regions by introducing a constraint matrix C, such that a user can easily encode geometrical interaction between different regions. So we tested our method on several applications, several organs, or different image modalities, but because I have short time, I just go through 2 of the experiments. So here's an example of cell segmentation in a microscopic image. The middle image is the results obtained from DeLong and Woodcock's method, and the right image is our method. So let me just talk about metrication error here first. So what is metrication error? Metrication error is a grid artifacts that occur in graph-based techniques. And that's because graph-based method penalizes the region boundaries only across axis-aligned edges. So that's why we see some blocky effect in discrete techniques or graph-based techniques. Whereas our method is free from metrication error because we use continuous framework. Also, our method segments the same image with 22 times less memory usage. So to segment this image, we set the thickness constraint between the different regions of these cells to be 2 pixels. But by changing the thickness constraint, we can choose which object to segment. So as you see here, we have 2 abnormal cells here with a thin thickness or thin distance between their boundaries. So if we set the thickness to 10 pixels, we can get rid of these abnormal cells. So again, our method used the same amount of memory as before, but Yelang and Boykov needs 313 megabytes extra memory if it wants to impose thickness of 10 pixels. To see how our method works on noisy images, so we applied our method on brain dynamic PET data. So in dynamic PET, each pixel is associated with a time activity curve, which time activity curve describes the metabolic activity in each tissue. So if you just rely on time activity curve and want to segment this noisy image, the result would not be anatomically correct. So we know that white matter, red, contains putamen, yellow, or putamen, yellow, and cerebellum, green, should be excluded from one another. And it's clear that this segmentation obtained from random walk method is not anatomically correct. If we encode these constraints, that we know that in brain, skull contains white matter, gray matter contains white matter, and putamen and cerebellum are excluded from it. If we encode this information, the result would be improved, and it's anatomically correct. So where we are standing compared to popular and state-of-the-art methods. So our method can encode containment and exclusion. It can encode 3 different spatial distance. We don't have any metrication error, and we can handle any arbitrary number of regions. The shortcoming, however, is that we cannot guarantee the globally optimal solution. So this, the solution, we need to convexify our formulation. So to convexify our formulation, we change the representation. So we replace the level set representation by a labeling function U. So this is just for simplicity, I just show for a 2-region object here. We show that by controlling or limiting the speed of changes in these labeling function, we can impose a thickness between different regions. And we can ensure that regions contain each other, for example, or even detach or exclude from one another. So, so this limitation can help us to encode these thickness constraint and geometrical interaction. So therefore, our energy functional consists of 2 terms, regularization term and data term, and we limit our labeling function to the set D, which takes care of imposing this constant, geometrical constant of this. So although the regularization term is called variation, which is convex, but the data term can be non-convex. How to convexify this term? So we use functional lifting technique. So the whole idea is to transfer the function to a higher dimension where it becomes convex. So we represent U in terms of its super level set, which we add another dimension to it, gamma. When we rewrite everything in terms of super level set phi, then the objective function becomes convex in phi. And as you can see, the non-convex part here, rho, now can be considered as a constant for a new optimization. But we have 2 absolute values here, and these absolute values cause some discontinuity when we derive the Euler-Lagrange equation. The standard way to deal with that is to define a dual variable and replace absolute value with a maximization problem. So after doing that, we end up with this objective function, which is continuous, convex, and we can encode these thickness or geometrical constant between different regions. So the results of our previous method depended on initialization. But in our new convex method, it doesn't matter how we initialize, every time we get the same solution. So we compared our method with Pod et al., which is a continuous method, convex method, but it does not encode any geometrical interaction between different regions. That's why the error is high in their method. And we compared our method with Gilang and Boykov, which is convex, can encode geometrical interaction, but it's discrete, and it's a graph-based technique, and it use a lot of memory compared to this. So our method can encode geometric distance constraint between different regions. It consumes less memory compared to its discrete counterparts. We don't have metrication error because we formulate our problem in a continuous framework. Our method consumes less memory and basically the memory usage and computation time do not depend on the thickness constraint as opposed to graph-based technique. It's parallelizable and we guarantee the globally optimal solution. So far, we focused on enforcing geometrical priors into segmentation frameworks. Next, we show how we can encode priors from different modalities into a segmentation. So in this work, we want to segment endoscopic video in robotic surgery. Several techniques have been proposed to segment endoscopic videos from threshold using morphological operation to level set, but the application of these techniques are limited again due to their sensitivity to noise and clutter in these kind of images. One recent method proposed to manually align a 3D model onto a 2D image, extract some features, and track those features over through the video. In computer vision area, non-medical applications, some recent methods propose to segment 2D images based on a 3D model. So the problem with these techniques is, so they either consider only rigid transformation for their model, which is not sufficient for robotic surgery because organs in the body can have non-rigid deformation. Or they design their problem to segment single object in a single image. Again, this is not sufficient for robotic surgery because we have at least a stereo video and we might interested to segment multiple objects. And both these methods cannot handle large occlusion when the object is occluded in the 2D image. So our solution, we noticed that when surgeons look at the endoscopic video, they have a CT on their head, CT from the preoperative day. So to distinguish different structures, surgeons basically manually overlay this CT information onto the endoscopic video. So we want to mimic this procedure and we want to automate this process. So after we take the CT scan, we segment the organs of interest. Now we have a 3D model. Then we transform and deform this 3D model in 3D such that its projection delineates the boundaries of objects in the 2D image. So the transformation parameters we use consist of two sets, pose parameters and shape parameters to handle non-rigid deformation. So we define a residual or error here. Now the goal is to find the most probable transformation parameters given this error. So to solve this problem, we using Bayes' rule and rewrite this maximization problem as a minimization problem. This second term allows us to encode prior on camera or tissue motion into the segmentation. How to solve this minimization problem? We take the derivative, set it to 0. The problem here is that the error we define is not linear with respect to psi. So we use first order Taylor approximation to linearize our error, and at the end we end up with this equality. Everything is known except this delta psi, which can be calculated efficiently. So we tested our method on 2 data sets. Here's an example of our method on a phantom lamb kidney data. What you are seeing here is the overlay of a 3D model onto a 2D image, 2D video. So green, yellow, blue are kidney, external tumor, and internal tumor. And these big black and plus sign that you see sometimes in the video is the artificial tool that occlude the object. So in the first row, we apply motion prior to our framework. In the second row, we don't apply motion prior. And as you can see, when the object is occluded, we lose the track when we don't apply motion prior. Whereas in the first row, we can keep the track. And here's our result on a real clinical case, partial nephrectomy. Again, in the second row here, because the tools occlude the object, we lose the track if we don't apply a motion prior. Here, when the surgeon moves this tool, yeah, we lose the track because the object's been occluded. So our method can segment multiple objects in multiple 2D images simultaneously. It can encode patient-specific prior using preoperative 3D data, and can handle non-rigid deformation. It can encode camera motion prior, and we propose a closed-form solution for our problem. So to summarize, in our first contribution, we tried to delineate the boundaries of overlapping multi-region cells using tri-base algorithm. In the second contribution, again, we wanted to solve a similar problem, multi-region object segmentation, but this time we improved the time and space complexity by leveraging the level set framework, augmenting it such that it allows to encode geometrical and distance constant between different regions. In the third contribution, we turn our attention toward optimizability. We propose a continuous convex formulation to segment multi-part object segmentation, multi-part object. This time we guarantee the globally optimal solution, and in our fourth contribution, we propose an efficient multi-work and segmentation method for segmenting endoscopic videos, and we encode motion and preoperative data into our segmentation. We also had a concrete overview of different types of prior knowledge devised in image segmentation literature, and we created an online database which is interactive, so we categorize different papers based on different priors they've used. And this is an interactive website, so researchers can contribute to make it up to date. And at the end, I would love to thank my senior supervisor, Dr. Hassan Havarner, who taught me a lot and guided me through my Ph.D. with patients, and also my Dr. Greg Mori, my supervisor, as well as my defense committee, Dr. Klaus Tanius, Dr. Pintan, Dr. Mark Drew. Thanks so much for accepting to be my defense committee. My colleagues at image-guided robotic surgery team, Dr. Rafti Tabakariye, soon to be Dr. Warzan Khalili, Dr. Jean-Marc Berat, and my lovely friends and colleagues at Medical Image Analysis Lab here at SFU. Thanks so much. I would welcome any question at this time.
Lovely talk, thank you. So Dr. Tanius, it's traditional in our examination schema that we start with the external examiner and then proceed with questions from the internal examiner, and then any committee members, and finally the senior supervisor. Then we allow people from the audience to ask questions if they have any. And then if there are any further questions that anyone would like to ask, we go through the whole thing again, meaning with yourself, Dr. Tanius, and then Dr. Pintan, and Dr. Mori, Dr. Nari. So if you could start with your own questions, Dr. Tanius.
Okay, thank you very much. It was very, very nice talk. I like the thesis very much. Let me start with a fairly general question. When I read the thesis, the first three parts, 1, 2, and 3, they seem to be like a sequence. Everything is better than the segmentation before. Is this really a sequence? That means, do I have to forget everything after reading the third chapter about the method that you presented previously, or are there reasons for it to go with a non-convex solution or even a heterogeneous solution such as the one presented in the first chapter?
There was a sequence actually, that's right. But although it improves in some aspects, the previous works, but they had some limitation as well compared to the previous work. For example, when in the convex formulation term, we only can encode a minimum distance between different regions, whereas in level set-based method, we could encode minimum, maximum, and some spring-like distance between different regions. Actually, it seems that encoding like maximum distance between different regions is an NP hard problem. So probably it's hard to have such like maximum constraint into a convex formulation. So I would say it depends on the application, that which technique to use. So in some applications, if we want to encode maximum distance prior or spring-like distance, the second contribution, the level set, would be more suitable. If we just want to encode like minimum distance, then I would say that the third contribution, which had a convex formulation, would be suitable because it can guarantee globally optimal solution. Yeah.
Okay, just one addition to that. The big difference in convexity, non-convexity, and also I asked myself, don't you think that from time to time it is even wish that the solution is non-convex? Because convexity means that everything that you want to optimize is really into your equation.
That's right. And that's a very good point. Actually, I agree. So sometimes non-convex formulation would be desirable because they probably can describe or model the problem more accurately. For example, in the second and third contribution, the level set and the labeling function, we cannot actually delineate the objects, the boundary of objects of that potentially overlap. Whereas in our first contribution, the genetic algorithm, well, it was very complicated fitness function, it was hard to optimize, it wasn't convex, but we could get better results because it could actually delineate the boundaries of objects when they overlap. So I agree that sometimes non-convex objective functions would be desirable because we want to model our problem as accurate as possible. So I agree. That's right.
Okay, and also there, you had always a solution where you really wanted to have something automatic because it had to be fast or you had to be lots of time.
That's right.
There are also a lot of cases where people, they don't have the time to interact, and well, sometimes it's easier to let the interactor do his input by initialization, and therefore you're not really interested in the optimal solution, just the solution which is close to the initialization.
That's right.
Regarding the genetic optimization, since it was very, very heterogeneous, the different features that you used there, I asked myself whether it was possible to find out when you used that which of the features were the most relevant for your segmentation success. Is there any way to make a quality assessment there?
So if I show this example, for example. The difference between, so based on the application, some of the features would be more important. So basically, for example, in this particular case, the edge polarity that we use, the edge polarity can distinguish between bright to dark and dark to bright edges. So this helps us to segment this image more than other, basically, more than other priors that we use. So I would say, again, it depends on the application that which prior is needed. So, for example, for these multi-region cells, and the geometry interaction that enforce containment, as well as edge polarity for this specific example, would be very helpful. And if you want to see which, or have a general, basically valid evaluation of how these priors contribute to segmenting the data, I would say, yeah, again, it really depends on the application, because sometimes we know that the shape of the objects are known, so we know that the shape should be circular. So definitely shape is very important to encode, or use edge polarity. But for some application, shape might not be a good descriptor, basically, because they might have some. For example, in neuron images, in neurics, basically, they might have different shapes. So probably shape would not be a good descriptor for that application. But again, there's a containment constraint on that images. Like in there, we have a myelin sheath and then axon. They contain each other. So these containment or geometric interaction would be more helpful to segment that. So it's really application dependent.
Okay, could this be feedback to the user? Because the things that you just explained there, that were by means of understanding the problem, making good guesses what would be important, also important. But sometimes it's the opposite. You just throw everything on the problem, thinking of, okay, that might happen, that might help. And you would be interested to find out what's really relevant in there. And since the genetic algorithm that produces some kind of quality, I asked myself whether this quality can also be used to estimate the success of the different parts of the features there.
So to see which prior is. So if I understand your question well, so you mean that we need to have a feedback to a user and see and let him or her know that which prior is useful, right? So automatic.
Yeah, yeah. Let me explain the reason for that. The problem that we have with segmentation is that sometimes it should be the person who actually uses the segmentation makes the major input in developing the method, not us, because it's not very efficient if they ask us every time. And if so, then I need to give him feedback because this person has not the kind of experience that you have when you decide what would be important and how they would play together. So everything that gives feedback on the quality of the result would be nice to have.
That's right. So one of the approach to this problem would be that we can show like different priors, like what we have here, to a surgeon. Not surgeon, clinician basically. So and then like for example, if they know that the objects of interest has like a specific shape, then they can click on shape and specify that property. So basically, again, by showing the priors that we can encode in an intuitive way, not very technical. So just by images, like I'm assuming it like showing as a very visual menu, so clinicians can click on different priors based on their knowledge, because they should ask this question from themselves: that what makes me distinguish different cells, for example. So obviously it's the shape, or so I would say by showing some visual menu and then let them choose, they can encode different priors. But how automatically choose these priors? One approach would be based on learning. So, for example, by segmenting a lot of cells in different microscopic images, we can train a system to learn which prior would be useful for segmenting cells, for example. So in that case, maybe we don't even need to ask clinicians.
That would be ideal. Okay, thank you for the moment. I think that somebody else might also have a question.
Thank you, sir.
Thank you. Now we'll go on to questions from the internal examiner, Dr. Ping Kat.
Firstly, I'd like to say sorry. I delayed your presentation significantly, but you still give a very good presentation, which is very impressive. You have a very short, limited time, and this happens suddenly. You still make a very good presentation. My first question is actually very similar to the question asked by the external examiner. Basically, I want to know if the convexified combination can be applied to the other first two cases. They have sort of addressed that question. So I want to further that question. Basically, I want to know, in your opinion, what would be the next direction to further this medical image research? Do you think it's worthwhile to try to convexify more of those constraints, formulations, so that you can guarantee a global solution, or do you think it's more important to design more appropriate priors according to shape or appearance to get the problem better formulated? So which one do you think is a more important direction for medical image segmentation?
So that's actually a very, very important question. So I'm thinking that like one of the reasons that convex formulation might be useful is that we can limit or sometimes even eliminate the need of interaction between the user. So because the good thing about convex formulation is that it doesn't matter how we initialize, right? So basically that could be very suitable for clinicians because they don't need to interact with the software, for example. But I agree that we cannot, or at least till now, we cannot convexify everything, and using a convex formulation, but not very faithful, like not very, we can simplify the objective function to make it convex. But this simplification might not be suitable. Even if we get a below optimum solution, that solution might not be the solution that we are looking for, because we simplify the objective function to make it convex. So, so I would say every time that we can have both fidelity and optimizability at the same time, it's better to convexify. If not, then we should focus on modeling, even if it's not convex, to get a good result.
Okay. My other question is regarding to your first application in segmenting overlapping cells. Can you give a little more details about how this is optimized? I suppose you require some user interaction or some sort of initialization of the genetic optimization.
That's right. So here, how we apply our method to segmenting a cell. So here we have an input image. So we spread a lot of solution or population all over the image, and to limit the search space, we only spread the population where the probability of existing cells are high. So that's how we limit the search space. Then each individual within a particular distance from one another establish a tribe. After convergence, we examine the best individual at each tribe and check its fitness value. So a fitness value here can be considered as a confidence measure. So we can keep only the top 20% of cells that have like 20% of fitness value. So basically, this is how we initialize. And then the thing is that the genetic algorithm has a randomized algorithm, and so every time that we run the algorithm, we might not get the same result. That's the disadvantage. But we did a further analysis, basically, to see how if our method is reproducible enough. So we ran our method 20 times for each image and monitored the fitness score as well as dissimilarity coefficient to see if we get a similar results. Well, obviously it's not the same, but at least we see that in these 20 times, the algorithm converges to the almost similar solution.
I don't have more questions at this time.
That's fine. Thank you. Thank you, Dr. Tan. So today Greg Murray cannot be with us, and I'm representing him. And I'm asking some questions that he had, and I'm actually making a subset, as I'm allowed to do. I have a suspicion that most of these questions have already been asked, or overlap most of the questions, but still. So the question is, how are the weighting parameters of the various terms in the fitness function, equation 3.9, how do you set the parameters? Yeah.
Right. So for this particular fitness function, we just basically apply the same way for all terms, and we didn't actually make one term stronger than the other. But for other contributions, like the level set, we learned those ways for containment, exclusion, regional term, regularization term. We learned them based on the training data. But for this particular, for the first contribution, because we didn't know which prior is better than the other, we couldn't actually weight them.
Sure. Okay, that makes sense. Maybe this has already been asked as well. What are the important factors in designing the GA-based optimization strategy? For example, to the tribes matter that we have mentioned. The chapter doesn't seem to examine the importance of using GA-based optimization. No ablative experiments, I think that means sort of distinguishing experiments, are conducted to determine which aspects of the GA-based optimization are important.
Which aspect of
The GA-based optimization are important. What?
Right. So the good thing about GA is that it can enable us to have a very complicated objective function without being worried about like whether it is differentiable or not, or can be take a derivative. So that's a good thing about genetic algorithm, that enables us to design any arbitrary or any complicated objective function without being worried about the derivatives. And also, so another good thing about genetic algorithm is, so basically, because it's a randomized algorithm, although it does not guarantee the global optimal solution, but there's a good chance to get a global solution, even if we initialize very far from this solution because it's randomized. So this is also an advantage.
Yeah, that's a good answer. The comparison with DeLong and Boykov notes that the increased memory usage for DB is for global optimality. This seems to be a third. I think it means there seems to be a third dimension, accuracy of results. Actually, I was wondering about this. Are there any results comparing your method with DB in terms of accuracy?
Oh, accuracy. Yes. So here's an example of our method. We compared our method with with active counter without edges that cannot encode any geometrical interaction, and with the DeLong-Boykov method. In this example, we want to segment these three region objects only. So of course, active counter without edges cannot solely segment that because it cannot encode any geometrical construct, but DeLong-Boykov can. And in figure C and D, we see the metrication error because in DeLong-Boykov if we use 4 connectivity setting or 8 connectivity setting between different neighbors, we get this metrication error. So these cause some inaccuracy in their method. Also, we tested our method with we actually quantitatively compared our method with DeLong-Boykov, again with 4 connectivity and 8 connectivity, and reported the dissimilarity coefficient. So here I reported the dissimilarity coefficient for our method and Ulen et al. So this Ulen et al. Also, it's similar to DeLong and Boyko. It's a graph-based method, but with improved optimization technique. So they are pretty much the same, graph-based, and so as you can see, well, the dye-similarity coefficient is pretty similar between their method and ours, but yeah, the thing that is important is memory usage basically.
Yeah, okay, I see. Second last thing, the work on real-time endoscopic video segmentation is very interesting. How would you envision the automatic segmentation being used in a system with the surgeon in the loop? What type of feedback would the segmentation provide, and what level of accuracy do you think is needed for this feedback? What about throwing it in the clinician?
Right. So actually, in our method is not fully automatic. So to have a, like if I bring this slide here, right. So here, we like to overlay or to transform the 3D object in 3D such that its projection delineate the boundaries of object in 2D image. We need to have a probability of different tissues in the 2D image. To get this probability, like for kidney, for tumor, for background, we need a feedback from the surgeon. So what we suggested actually is that surgeon can use their tools as a virtual brush to just roughly brush over kidney or tumor and background. So we have some seeds, and then we calculate this probability. So we need surgeon in the loop, definitely.
Yeah, okay, that's already there. So the last question is not a question, it's a statement. Dr. Mori says, this was a very strong thesis and I enjoyed reading it. Congratulations to MASOUD on an excellent Ph.D.
Excellent.
Now we'll proceed to questions from the Senior Supervisor, Dr. Convexity.
All right, thanks, Mark. Well, thank you. It's very good presentation. I enjoyed working with you and your thesis. I think it's really good. So many of my questions were covered and asked even before. So maybe just a few questions related to the convexification. So the functional lifting and the primary dual representation and so on. So you convexify the energy. So what do you lose? What do you lose in that method?
So the whole goal on that contribution was that still keep the objective function faithful, like we still want to encode geometric interaction. So we didn't want to lose that aspect. So that's why we wanted to improve both fidelity and optimizability. But what we lose there compared to our previous,
not compared to the previous method, just
compared
to
itself.
before convexification and after. Is it just a free lunch? You can convexify.
I see. So basically,
yeah, exactly.
so the difference between these two.
Yeah,
what we
before the
lose-
green and after.
Right.
Before